So I'm going to talk about energy and the tensions in the energy landscape, starting with renewables, how we can meet the growing demand of electricity in things like data centers and electrification things. This is not me alone, it's primarily the work of folks over here that I'm relaying to you. I couldn't do anything without our excellent team at the Western Cooling Efficiency Center, so I'm specifically highlighting these people whose work I'm presenting today, but there are lots of students and other engineers at the center who have been involved. We have an excellent group of affiliate companies that sponsor our work at the center, and we can't thank them enough for supporting our work on a continuing basis. Our research is sponsored by a bunch of agencies, primarily the Department of Energy and the state of California, California Energy Commission included. So I'm going to talk about the renewable energy landscape and the energy landscape in general. On the left side, what you see is from the IEA's data of the electricity generation in the United States, going back to the 50s. You see that there was a steady climb, but then in the last about 2005 to 2018, the electricity generation has been about steady. And the reason for that are many, but primarily related to the decrease in industrial production, flat residential energy consumption, and energy efficiency measures. But the projections going on in the future is what's shown on this plot here. And we are over here, and we see that there are about 4,000 terawatt hours of electricity, but we are growing steadily for the next up to about 2050. And the good news is that there is a big increase in the renewable energy generation for electricity, double. But bad news is that we are still using a lot of natural gas. So we can ask ourselves the question of two questions here. Why is natural gas still going to be an important fuel for our electricity generation in the future, all the way up to 2050? And the second is, why is this electricity increasing while it's been flat for several years? So the first one, let's ask ourselves the question of, do we have enough renewable energy resources in the country to power electricity for all the way up to 2050 and beyond? So if you look at this map from NREL, the United States is blessed with a wide range of renewable energy resources and options. We have wind over here, and ocean energy. We have solar in the yellow, and then we have a combination of solar and wind in the Midwest, in the middle of the country. So there's plenty of sources, but of course you have to rethink how you generate it, how you transmit it, and how you store energy, because those are going to be intermittent resources. If you look on the left side here, this is the amount of energy that you can technically extract from the renewable resources. And technically extract means, okay, we are looking at topological constraints, system performance constraints, and the potential is vast. Just with solar alone, you can look at about meeting over 100 times of the demand of electricity. So why is that not happening? Why do we still need natural gas in the future? That's because of the economic and market potential. It has to be competitive with natural gas, and natural gas is really cheap now. So that's why going into 2050, we still use a good chunk of natural gas. So going to the next topic of why is electricity demand increasing by a lot? There are a bunch of reasons for that. Good reasons. On the left-hand side here, we have a rebirth of industries, and that's adding demand to the electric grid. And these industries are clean manufacturing industries. So the IRA map taken from this month shows a whole bunch of new companies or new industries coming on board in the next few years that requires more electricity. Over here is the growth of data centers with AI and ML. It's huge. If you look at estimates by the Boston Consulting Group, right now we are about 2.5% of the electrical energy in the United States is used by data centers. By 2030, it's going to be threefold increase. 7.5% of the electrical energy in the United States is going to be for data centers. That's equal to powering 40 million homes. In London country, in Virginia, which is a data center alley, due to this great fiber optic infrastructure for low latency, the The estimate conservatively is that by 2032 they need 7 gigawatts of electrical power. That's like 7 mid-sized nuclear power plants, just for that count. So that's one big thing. The other drivers, for example, in California, is electrification. Electrification of buildings, transportation. That is a huge driver in increased electrical load. What I'm showing here is what's happening in buildings, but I want you to note that for transportation, it's about 3 times higher in terms of the load. Over here is projections of the CO2 reduction due to electrification in California. So these reductions are happening because of fuel switching. So if you have furnaces at home, you're replacing it with heat pumps, but also heat pumps have used global warming refrigerants. So it includes reduction in refrigerant GWP as well. So all that put together and some energy efficiency measures, we are looking at 19.6 billion metric tons of reduction in CO2 by 2050. But what that also means, and this is the tension, is that we need more electricity. And over here you see a plot of the green and the blues combined is the energy that you need because of electrification. Thankfully for us, we have energy efficiency measures in place, and those energy efficiency measures will mean that instead of needing 25,000 gigawatts hours by 2035, you only need about 10,000 gigawatts hours lower. So energy efficiency is a huge and very important part of this scenario. So let's talk about heat pumps, because heat pumps are important to drive down CO2 emissions and go towards electrification of buildings. But if you've seen in the previous slide, the goal in California is at 6.35 million heat pumps in place by 2030. Over the past 9 years, we have only gotten 1.4 million heat pumps in place. It's growing, but there are still some barriers to heat pump adoption. So if you look at those barriers, the first barrier is that you need to have an increased panel capacity, electrical panel capacity, and that's a big barrier for heat pump adoption. And the reason why you need electrical panel capacity is, unlike in a traditional air conditioner, you can't just swap out a traditional air conditioner for a heat pump, because during the cold winter times, you need to have an increase in electrical capacity by way of strip heating. Let's say the outdoor is really cold, the outdoor coil will get iced up, and you need to reverse the cycle to defrost it. And when you do that, you're running an air conditioner during winter. Not nice. So you've got to provide strip heating to keep the occupants warm. And that tanks efficiency, and you need to have that extra panel capacity for the strip heating. So that's a big downside. There are also other adoption issues. Sarah Arncourt and her group have done a great job of looking at the market barriers to heat pump and what methods you can use to alleviate those barriers. Low observability, low trialability, complexity of installation, comparing quotes between different installers. All these are really hard market barriers, not engineering, but they need to be considered. So here are some of those barriers that I've noted here and the solutions for them. But I'll focus on one potential solution, technological solution, which is a multifunctional heat pump. The idea is, can you have one device that does everything? It does heating and cooling of the space conditioning, basically, as well as water heating. And can that device help you get rid of that panel capacity problem? So a multifunctional heat pump works like a traditional heat pump for space conditioning, but it also does water heating. And since the water heater tank is like a thermal storage, you can rely on that for defrosting rather than putting strip heating over there with the air handler. So that's the basic idea behind it. And our group, a whole bunch of engineers are working on this problem. Here is an example of a time series of what happens when you have a multifunctional heat pump in operation in a real house. This is the indoor, this is the winter time. So the blue is the outdoor temperature, the green is the outdoor temperature, and this is the indoor temperature, it's maintaining it steady. This is the water tank temperature. So let's say you have a cold winter morning, the the defrost cycle kicks on, and instead of using strip heating, it uses the water tank, and it draws heat from the water tank to defrost the outdoor coil, and hence you kind of alleviate the problem of having that extra heating, electrical heating. So that's multifunctional heat pump. We are working with a bunch of companies to take this technology forward. Now I talked about global warming potential refrigerants being a problem, and over here on the top left I've shown some GWP numbers for refrigerants that are used in these heat pumps and air conditioners. We have a mandate in California of going to less than 750 GWP by 2030, but eventually we see down the road that we'll have to use natural refrigerants to get away from this GWP problem. So natural refrigerants, we are talking about propane, for example. It's a very good refrigerant for heat pumps, but it is flammable. So almost necessarily what you have to do is use a secondary loop to bring heating or cooling into the house if you use a refrigerant like propane. And what I mean by that is you contain the refrigerant propane inside this heat pump, it comes factory sealed, and then you have a secondary loop where the propane exchanges heat or cooling with the secondary loop like glycol water, and that flows into an air handler and provides the heating or cooling to the house. The issue, the tension here is that the secondary loop adds inefficiencies and you lose performance based on the having additional heat exchangers in the process. What we have done is we have looked at this tension and we looked at the solution for it. The biggest bottleneck in the secondary loop is that you're using heat exchangers like what is shown here. Basically a bunch of tubes and then fins that you blow air across it, you have the glycol water going through the tubes. And this has been in business for decades. Industry makes this all the time. But a cross-flow heat exchanger is not a very good heat exchanger. The best heat exchanger is a pure counterflow heat exchanger. So we thought about that idea and we said, okay, if you go to a pure counterflow heat exchanger, the bottleneck for heat transfer is on the air side. So you don't even need to use metals. You can use polymers and get a better heat exchanger made with a polymer if you have a pure counterflow heat exchanger than if you have a cross-flow heat exchanger like this. So we are moving from here to this is our design for a pure polymer-based counterflow heat exchanger, and our models and experiments show that we get much higher heat transfer to air using a plastic heat exchanger than you can a metal heat exchanger. One of the things I mentioned when I talked about the California electricity demand in buildings is that we have a lot of energy needed, but energy efficiency can help. So this is one of the technologies that is developed at the center, has been very successfully commercialized by our former director, Mark Madeira. The idea is to seal the building envelope automatically. And so the idea is to put aerosols with a sealant in it, in liquid form, and you depressurize the building, you spray it in the attic, the aerosols go through the leaks and seal the leaks, and hence you can have a tighter envelope. And a tighter envelope means basically that you're going from a 15 air changes per minute of 50 pascals to about 7 for the ones that we tried, and that results in about a 20% reduction in heating and about a 5% reduction in cooling loads. I want to move to data centers. Oops, I see you red there, but it's important. On the top left here is what's called the power use effectiveness of a data center. So basically, all the electrical energy going to the data center divided by the electrical energy going into the servers. It's not a perfect metric, but what you'll see is that over the years, the PUE has gone down, and it's about 1.5. That means 50% of the energy is still used for other things than compute. And that's not good, because we are expecting 390 terawatt hours of electrical energy going to data centers by 2030. So ARPA-E has a challenge for us engineers, and they told us, can you reduce the energy used for cooling? A lot of energy is used for cooling in these data centers. They just cool down the entire data center room so that if you walk into a data center, you've got to go with a thick coat. It's that cold. And there are better ways to do it. The chips, CPUs, GPUs can handle temperatures So why do you need to cool the entire data center down? Why can't you go to the source, which can handle temperatures of 80 degrees Celsius, extract heat from there, and just dump it in the environment? At best, it's going to be at 45 degrees. You still have a delta T to transport heat. You don't need to chill the building down. That's the idea. So if you can get down the electrical energy used for cooling from 40% to 5%, that's the challenge given to us by ARPA-E. You can have tremendous savings. You're going from 390 terawatt hours to 253 terawatt hours doing that. That's equivalent of removing a dozen power plants from the grid. So our concept is shown here. It's a modular data center, highly dense modular data center. So imagine a 40-foot shipping container volume, and imagine having 1.5 megawatts of compute in it. That's the kind of density we're talking about for the future of data centers. Too much to talk about here. So I'll stop here and be open to questions.
What are the prospects of small nuclear generation?
Glad you asked.
And what is the time frame? Because my understanding the time frame is beyond what is that?
In other words, they're unreasonable because simply of regulation.
Regulation. So when I was at Oregon State, there was a company that started up NuScale that makes small modular reactors, and this was 15 years ago. And they are still in the regulatory process, and I think they finally got their approvals. So it's a very long time frame for small modular reactors. But if you look at this pie chart, I can talk about it in detail. This is a chart by Uptime Institute. They talk about renewable energy and cooling as the two biggest drivers for sustainability of data centers. I was talking about the cooling aspect of it, but renewable energy is a huge aspect, and a lot of companies are partnering with small modular reactor companies to power their data centers in the future. They're developing those partnerships.
Good questions? Can I say something? Thanks. I'll ask a question since we have a minute.
Thank you, Vinod. It's so creative to see what you're doing, tackling multiple problems at the same time. And it's just very inspiring. And I was just wondering if you could say a little bit about that tension between decarbonization through electrification and the use of energy.
Yeah, so that's the hard one, right? So we have to combine, we can't do it just by electrification alone. We have to also combine it with energy efficiency measures so that we drive down the number of renewable energy power generation systems that are needed.